He has negative things to say about it.
Yeah.
Oh, you haven't taken it yet. That's not bad. I like that. I tasked Madison with it too.
It's like
A small, real big for you. You don't leave this. Make eye contact. I'm gonna leave this unscrewed in case I need it. She'll be there for me.
What is?
Are you?
Space pouring here.
Oh, okay.
You're not expecting. They're always looking. Good evening, ladies and gentlemen, and welcome to Astronomy on Tap Atlanta. Thank you for coming, even with the risk of thunderstorms. We really appreciate it. Our old friend, the telescope. Why is this revolving?
It's for epicness.
Test 1, 2. Test 1, 2. Test 1, 2. It's gonna sound really spacey tonight. Is that okay?
That sounds amazing.
Alrighty. So tonight, our guest is Georgia State University Astrophysics PhD student Madeline Davis. Let's give her a round of applause. Madeline Davis works under Dr. Michael Crenshaw over at GSU, a very special old man to my heart. He was on my PhD committee, and he is now guiding her along her research in the mass outflows being accelerated through their galaxy by the feedback of supermassive black holes. Be sure to join us next month for our 2-year anniversary, and I come back and talk about the first images of black holes that we ever got. But in the meantime, you guys showed up for an alien summit. So without further ado, everybody, one more round of applause for Madeline Davis.
Hello, everybody. So, like Justin said, my name is Madeline Davis, and I am very excited to talk to you all today. So, our topic today is life in the solar system, with a big question mark there. But I think since I'm a life form talking to you here as other life forms, we can go ahead and remove that question mark and say life in the solar system. Yay! Yes! Thank you, everybody. Yeah, so it does in fact exist, and I'm being a little facetious here. Like, obviously, we're here to talk about life outside of Earth. So, in order to do that, we kind of need to go back to the beginning, and not just the beginning of Earth or life on Earth, but the formation of the solar system, so we can understand how that all happened and how we got here. So, the solar system is 4.6 billion years old. And this is a great, diagram of how it sort of formed. So over here on the far left is where we started. And the sun and everything around the sun that formed our solar system started out as this really, really big, massive cloud of gas and dust. And now what was inside of this cloud of gas and dust was mostly hydrogen and helium, but there was also trace amounts of lots of other things like carbon, oxygen, phosphorus, sulfur, silicon, nitrogen, beryllium, lithium, all these extra elements that you see on the periodic table, they did exist in this cloud, just not in as large amounts. And this cloud started to collapse. Something triggered it to start to collapse. So it also had a spin. And so as it collapses, it spins faster. And that's how you start to get this disk formation. So when things spin and collapse, they start to form a disk. And as you can see in this stage, the second one, there's a disk here. Things are starting to sort of cool around the outside of this disk. And there's a little, what we would call the proto-sun, or prior to the sun in the middle. And this is before the sun has started fusion in its core and officially become a star. So there's things starting to cool, starting to coalesce. And then in the next phase is when we have our sun start fusing hydrogen to helium in its core. And this is a very powerful event. So that causes a shock wave to be sent out throughout the solar system and sort of is able to push a large amount of those lighter elements like hydrogen and helium to the outer parts of the solar system to eventually become the gas giants. And in the inner solar system is where we have the heavier things stick around, like rocks and dust and molecules that have formed. So all of these things start to stick together, and it's pretty violent. You'll have one rock hit another rock, and then another rock, and then another rock, and all of a sudden you have this ball that has some sort of gravitational attraction because it's gotten so big and starts to attract things from around it. It starts to clear out its orbit. It's pretty violent. There are tons of collisions going on. There's tons of gravitational interactions. Things are literally getting ejected entirely from the solar system as this is going on. But eventually, we have things start to calm down. Things have started to coalesce in their orbits and clear out their orbits. And then eventually, we are left with what we have today, which is a sun and planets and moons and asteroids and comets and all those good things. So I've talked about how the solar system formed, but now we need to talk about how life on Earth all began. Well, like I said, early Earth probably looked something like this: a big ball of magma that is just starting to cool because all of these rocks stuck together, and that's a lot of friction and a lot of energy. So things are really, really, really hot. But eventually, about 4.5 billion years ago. That's what that GYR means. It stands for giga years. That's what astronomers use to mean billions of years. So the solar system formed 4.6 billion years ago, and 4.5 billion years ago, the moon formed in a very violent collision. Basically, something hit us. Like I said, early solar system was chaotic, right? So really something really big hit Earth as it was trying to form, and that caused a chunk of the crust to be shot off of Earth's surface, and it started to orbit us and eventually formed the moon. Now, after this is a sort of chaotic period in the solar system that we call heavy bombardment. And on the surface of Earth, it probably looked something like this. So the surface of Earth has started to cool. It's a rocky surface, of course, but it is getting impacted by so much extra stuff in the solar system, notably asteroids and comets, that it sort of keeps the surface more molten than it should be in this stage. And there's tons of volcanism. There's tons of stuff getting shot up into the atmosphere. Very chaotic period of time for the surface of Earth. But that period ended about 3.8 billion years ago, and the oldest fossils that we have ever found are 3.5 billion years old. So this is the oldest fossil ever found, and it was found in Greenland, and it's a fossil of a stromatolite. And as you can see here, the stromatolite fossil are denoted by these dashed lines. And what this is a stromatolite is formed from the sedimentation and the buildup of little microorganisms called cyanobacteria. And like I said, this fossil is 3.5 billion years old. But it didn't just show up out of nowhere. It had to form. So it had to take time to form. And we think that the earliest life could have started to form was right at the end of the heavy bombardment period, 3.8 billion years ago. So funny enough, so stromatolites actually still exist today. This is Shark Bay, Australia. And these little rock formations are these stromatolites that we're talking about, and they still exist. So this is actually a great depiction of what we think early Earth looked like right around when life was starting to form. So talking about this fossil, but what did the first organisms look like? So they had to be the simplest form, right? We had to come from somewhere. So they had to have been single-celled. Simplest, most minute form or unit of life. And another thing is that at this time, Earth did not have a significant amount of oxygen in its atmosphere. So these organisms had to be anaerobic and do photosynthesis without oxygen, which is different from us. Another thing about planet Earth then is that it was hotter than it is now. It hasn't had as much time to cool off as it has now. So these creatures had to be thermophiles, or not only exist in extreme heats, but thrive in extreme heats. And thermophiles can thrive in temperatures up to 230 degrees Fahrenheit. So that's about how hot we're thinking early Earth was. So we've talked about what the first organisms could have been, what they could have looked like. So the next question that we draw from this is what conditions gave rise to the first organisms on Earth? Because if we know the answer to this question, maybe we can look for these conditions elsewhere. So we actually have a name for these conditions, and they are called the primordial soup. Yay! Yeah, so it's this funny little name, and you need some things for primordial soup. Right, so Avatar got it partially right. we did need water to form the primordial soup. And the important quality about water is that it's a solvent. So you need something that dissolves other stuff and allows things to easily mix around and allow life to form. Like you need things like proteins to start to form and like amino acids and RNA, and it can't do that unless everything's sort of dissolved and mixing together. So we have water, which is a great solvent. And then after that, you're going to need this acronym that if you've taken a biology class, you may have heard before in a different form, but I prefer the acronym CHOMPS. So what CHOMPS are all the elements that you're going to need for life. They are carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. All life on Earth is carbon-based, and every single basic building block of life has all of these elements. So you need CHOMPS, you need water, then you're going to need an energy source. And in our case, that's the sun. We're a terrestrial world. We're close to the sun. We get plenty of light from it. But that also sort of poses a problem. The sun is a very, very, very powerful energetic thing. So you're also going to need protection from its harshest radiation. So what's depicted here in blue around the Earth are sort of like magnetic field lines. So the early Earth had a magnetic field that is able to divert the sun's harshest particles like solar wind particles and cosmic rays, because those things are bad for life. They're super duper energetic, and if they hit the surface, they could easily break apart any important molecules or cells that are trying to form. So you need protection from these powerful rays. And in our case, we had a magnetic field because we have a magnetic field still. That would really suck if we lost it. And we have that because there's a spinning ball of iron and nickel that is our core, and it's spinning because it's in a liquid outer core, and it's spinning really fast and it's charged. And what you need to generate a magnetic field is spinning charge. So we have a magnetic field, and we also have this extra layer of protection known as the atmosphere. Very helpful for us here on Earth. And last but certainly not least, the last thing you're going to need in order for something to be primordial soup is time and stability. So, like we said, we don't 100% know how long it takes life to form, but we know that it could have taken up to a few 100 million years. It could have been anywhere from the very end of heavy bombardment all the way up to 3.5 billion years ago. And then stability, what I mean by that is you're going to need some sort of surface for these things to stick to. So you've got all these things, mixing around in this solvent, or, like water in our case, and they need to have a stable thing to stick to so that more things can stick to them. So these are all of the conditions we need for primordial soup. So the next question we need to ask is, where else could these conditions exist? Let's meet our contestants, everybody. Yeah. All right, so first up, we are going to talk about Europa. This is one of Jupiter's moons. After this, we are going to discuss the world Enceladus. This is an icy moon around Saturn. Next up, we're going to talk about another one of Saturn's moons, Titan. And then last but certainly not least, we are going to talk about our little friend, the red planet Mars. So just for reference, these are the true size comparisons of these worlds. For reference, Mars's diameter is about half that of Earth's. Europa over here in the top left is about the size of our moon. And as you can see, Titan is pretty big, especially for a moon, and Enceladus is pretty tiny. So let's meet these worlds. First up, we have Europa. So Europa is the second Galilean moon of Jupiter. What that means is that there's 4 Galilean moons, if you haven't heard of them before. They're just the 4 big innermost moons of Saturn, and they're called Galilean moons because they were big enough that Galileo was able to discover them with his telescope many, many, many years ago. And another thing about Europa is it is very similar in size to our moon, like I said, and it's an icy world. Very cold. It also has what we call a tenuous atmosphere, that just means unstable. Like the atmosphere isn't thick, and it's not always there. Sometimes it's there, sometimes it's not. Another thing about this is it has an induced magnetic field. So Europa isn't big enough or powerful enough, really. There's not enough going on the inside for it to generate its own magnetic field, but it exists within Jupiter's because it's so close to Jupiter, and Jupiter is huge. So it's actually able to steal part of Jupiter's magnetic field and use it for its own protection. And we're going to discuss why later. So I'm talking about Europa. It's an icy world. It seems like a barren place. Like it's frigid. It doesn't even really have an atmosphere. Why the heck are we talking about it? It's not even in the traditional habitable zone that we talk about where there's liquid water on the surface. So Well, there's more than meets the eye. So let's take a closer look at the surface. So like I said, this is a crust of ice. So there's obviously something weird going on here. You can notice a few craters, but the main thing about this is you see all these striations. And what these striations are, these dark lines, they are cracks in the ice. And what that indicates is there's got to be something going on underneath. The Earth's crust moves and there's magma underneath. If this icy crust moves, there must be water underneath. So this is a diagram of the inside of Europa. And one thing about Europa is it has global oceans of liquid salt water, which is pretty crazy. Another thing it has below that, well, you know, it has liquid because it has to be heated from below. It's not getting heat from above. So that means it's getting heated from below by the rocky, you know, outer core, which has hydrothermal vents. And so there's a lot of cool stuff going on here. And one of the things about this liquid salt water ocean that I'm talking about, salt has a charge, and it exists, this salty water exists all over, you know, the subsurface oceans of Europa, and Europa is spinning. And so this spinning charge is why Europa is able to steal some of Jupiter's magnetic field. Yeah, so we've got these hydrothermal vents, which is pretty cool. It's heating things from below. Interesting place. So you may be wondering, well, I don't know if you're wondering, but a weird thing about Europa is that it's still hot. This is a small world. Usually things this size would have cooled off by now. Like Earth is still hot on the inside because it's pretty big. Europa is way smaller. So there's an explanation for this, and it's tidal stretching. Basically, Europa is in the presence of Jupiter, and Jupiter is huge. And Europa's orbit around Jupiter is not perfectly circular. So there are different points in its orbit when it's closer or further, and things start to get stretched and pulled at different points. And that means there's friction on the inside, things melt, things heat up. What you're seeing here in this little video on the right is what we call an orbital resonance. And this is what keeps Europa in its, you know, non-circular orbit and keeps it from, you know, cooling down and stabilizing. And what an orbital resonance is as you can see here, so these are some of the Galilean moons. And the first orbit that you see is Io, the innermost of the Galilean moons. The second one you see is Europa. And when they light up, that is when there is a gravitational tug happening between those two worlds. So Europa is in a 2-to-1 resonance with Io. So for every 2 orbits Io completes, Europa completes 1. And what that does is cause some sort of gravitational pull at certain points in Europa's orbit, and that keeps it from circularizing and sort of keeps the interior hot, which is why Europa is able to have hydrothermal vents and subsurface oceans. So that's why it's still hot. Let's talk about if it has primordial soup. This is a schematic, everyone. Don't worry, it's not a photo. That'd be wild. So first up, we're going to look at, does it have water? Well, yes, it does have water. In fact, studies show that it actually has 2 times the amount of liquid water in its subsurface oceans as Earth does on its surface. Plenty of water. Next up, we are looking for that chomps. Does it have chomps? Not quite. It has chons. Like I was saying, though, at the very beginning, the cloud of gas and dust that formed the solar system had all sorts of things in it. So all of these elements that I'm talking about do exist in some capacity everywhere in the solar system. But in our case, it's going to be about how much and where in the world, and is it enough to contribute to the formation of life. Just because we haven't found it yet doesn't mean it's not there. That's why we keep studying these things. But yeah, Europa definitely has chons. So next up, we are looking for energy source. You may be thinking, that's a layer of ice. Don't tell me that the sun can get through there. It can't. I'm not going to tell you that. But what I will tell you is it has hydrothermal vents. So it does have an energy source. There are plenty of regions in the oceans of Earth where there are hydrothermal vents, and those areas are teeming with life. And they don't need the sunlight. They just steal energy from the heat that's coming out of these hydrothermal vents. Okay, so we have that. Next up, we're looking for radiation shield. Like I said, it does have a radiation shield because it's able to steal part of Jupiter's magnetic field for itself. And also it has this layer of ice, which is pretty helpful for blocking a lot of different things. Last but not least, we're looking for time and stability. Yes, it does have time and stability. It's had the same amount of time as everything else in the solar system. It's a very good approximation that everything formed at the same time. So that's what we say. And that's because that's what happened, we think. Okay, so you may be thinking, well, this looks kind of promising. It has pretty much everything. So like, why don't we go there? Well, we are actually. So we have a mission currently on its way to Europa, known as the Europa Clipper. It launched in October of 2024, and it will do a couple things. So it's a Jupiter orbiter mission, and it will get there in 2030. And it will perform about 50 very close flybys of Europa. So it'll be able to do things like, map the surface, look for plumes, find temperature variations. So like those cracks, there's plumes there. Water gets shot out. And what the spacecraft is going to be able to do is, maybe perform some spectroscopy on those plumes. It's going to be able to get that chemical composition fingerprint of what's going on in the subsurface oceans. It's going to be able to map temperatures. So like, how hot is it? Are there regions where the ice is thinner? The main goal of this mission is not to confirm or deny whether or not there's life, but rather confirm whether or not the conditions for life exist. There is a proposed Europa lander mission. It is not confirmed. I mean, we have to send the Clipper there first, figure out what's going on. But the purpose of this mission would be in a few decades, maybe determine if life exists there or not. Okay, so we've reviewed Europa. Next up, we're going to talk about Enceladus. So as you can see, icy world with these blue marks on it. And it is a moon of Saturn. It is pretty small. Icy world. It is actually the most reflective object in the solar system because of how white its surface is. Like, it's literally snow. And another thing is it's, small but mighty. It's about half the size of Texas, for reference, by the way. So like I said, it's small but mighty. And what makes it so mighty is this giant plume of ice and water. This little world is able to shoot out from its subsurface oceans at 800 miles per hour. And as you can see, it extends pretty far. This is a huge plume from, the pressure underneath. It gets shot out really far. And this plume has actually formed another ring around Saturn, known as the E ring. It has shot out for so much material for so long that it has formed another ring. So that's pretty crazy. So one thing I want to note about Enceladus is it has what we call these tiger stripes, and there are these blue marks that you see on the left side of this image, and we call them tiger stripes because it looked like a tiger just like kind of took its claw and like ran it down the side of Enceladus. And this is the South Polar region where that huge plume is coming from. This region is also the only place on the surface that we have found organic compounds, and that's going to be carbon dioxide. So that might be indicative of what's underneath. Okay, so let's talk about what's inside of Enceladus. So the layers from inside to out are probably magma, then a porous rocky core, then a global salty ocean, and crustal ice. So we've looked at the layers. Now let's talk about if it has the conditions for primordial soup. Water, yeah, it's got plenty of it. Next up, we're going to look at chomps. Does it have chomps? No, it has chomp. So it doesn't have sulfur. We haven't detected sulfur. That doesn't mean it's not there. We could always find it. Next up, we're going to look at energy source. Same kind of thing with Europa. Its energy source is going to be those sort of hydrothermal vents, that magma heating up the rock below. Next, we are looking for radiation shield. Does it have a radiation shield? Sort of. It's not big enough to steal any of Saturn's magnetic field for itself, but it does have tons of material around it that can help, reflect some of the harmful rays of the sun, and it has that layer of ice, which is beneficial. Okay, next up, we're looking for time. Formed at the same time as the rest of the solar system. It's had plenty of time. Then we're going to look for stability. This one is a little bit of a question mark, and it's because of the interior porous core. So on the one hand, porous rock, mixing with water could be really good for life. It could provide all these little crevices for, things to mix and dissolve and form in. But on the other hand, we don't know how permeable or perhaps mobile this surface is. So could things just fall right through? Is it harder for life to form? We're not 100% sure. So with that, we're going to move on to the next one, Titan. So this is an image of Titan. And actually here in the bottom right corner of this image, you can see a south polar storm. And that's because it has an atmosphere. So Titan is the largest moon of Saturn, and it's actually the second largest moon in the solar system by just a hair, 60 miles. That is the technical definition of just a hair, in case you're wondering. And this is another icy world, but it is the only moon with a thick atmosphere, and it has a water cycle analog, which is kind of crazy. Like this thing is far out, and why is it behaving a little bit like Earth? That's really curious. So this is a different image of Titan, and this is not what our eyes would see. The previous picture is what our eyes would see. Our eyes only see the atmosphere. Our eyes cannot, we don't have X-ray vision, guys. We cannot see through the atmosphere. Really cool if we could, but we can't. So we need to use telescopes. This image you can see in blue around the outside, that is in the UV, and that's illuminating the atmosphere of Titan, so you can see how thick it is. And then within that, you can see this pretty colorful image where there's some dark regions, and this is a map of heat in the infrared of the surface of Titan. So it gives you an indication about maybe some of the surface or what's going on. So I think personally that Titan is the weirdest place in the solar system by far. So let's talk about why it's so weird. One, it has an atmosphere, which is, like I said, it's insane. It has a thicker atmosphere than Earth when you compare it to the size of the world. The pressure on the surface is 50% greater than the pressure that you're feeling right now from the atmosphere. And also, this atmosphere is made of mostly nitrogen like ours is, but it also has methane, which is CH4. And that's what sort of gives it this hazy brownish orange color you see in this image on the right. So that's crazy it has an atmosphere. Next up, it has surface lakes. It literally has, sorry for yelling, everyone. This place is wild. Okay, it literally has liquid on the surface. No other world in the solar system besides Earth has this. It might not be water. It is methane. No, that is not true color. It's actually brown. The liquid would look brown to us. But like, come on. These lakes exist in the North and South polar regions of Titan, and they're pretty big. Like the top one there, Legia Mare, is about the size of Lake Superior. And come on, Kraken? Are you kidding me? That's pretty awesome. Okay, so it has lakes of the polar regions. That's the North Pole. This is a depiction of the South Pole. The lakes are not quite as big, but they are, more frequent. So it has surface liquid of methane, which is, it's a gas here, but because of the pressure of, the atmosphere and how cold it is, methane can exist as a liquid. So it's also weird because it has a liquid methane cycle, and this is an analog to Earth's water cycle. And if you don't remember what that is, let me remind you. So you should all remember this from grade school. So we have oceans and lakes, and water from those oceans and lakes can evaporate, and then it condenses into clouds, and then it rains back down on the surface. And that's the water cycle. There's also some groundwater movement going on. So Titan has the same kind of thing, but for liquid methane. So there are liquid lakes of methane that we've seen, and that stuff can evaporate, condense into clouds, and then rain liquid methane back down onto the surface. There's also some volcanism going on. There's probably some liquid reservoirs of methane underneath that are getting shot back out into the atmosphere. So this is a really, really weird place. And one other really crazy thing, we've been there. We landed on the surface. We're gonna watch a video. Okay, so what you're seeing here is this is an animation, but this is the Cassini spacecraft. This spacecraft was in the 2000s and 2010s. It was a Saturn system orbiter, and it had a probe on it named Huygens that was specifically designed to land on the surface of Titan. So it detaches, starts its descent, and it has a very, very thick atmosphere. So the captions are going to tell you things, but I'm also going to talk. Yeah, really, really long descent. And as you can see, as it makes its way through this hazy atmosphere, you see the surface start to come into view. The high regions are the light ones, and the darker regions are the lowlands. And yeah, remember, this is a surface of ice. It might look like rock. It behaves like rock because it's so cold, but it is literally ice. And it has this color, this brownish orange color, because that's the color of the atmosphere. So it's going to reflect that color. You can see things start to come into view. Maybe this was formed by liquid on the surface. Mountain, a valley, another mountain. 2-minute long video, guys. So soon here, it's going to switch views. You're going to see a different kind of video of the surface. That's the surface of Titan. That's a video. This is what our eyes would see. That's a ice rock. And it had a parachute. You can see the shadow of the parachute pass overhead. Guys, this is literally the surface. This is the farthest away we've ever landed. I think this is absolutely crazy. And as you can see, this rock is smooth. What causes that? Liquid erosion. We think this is an ancient lake bed because, I mean, you know, the video, you may have seen in the video captions, but astronomers thought that, you know, maybe Titan had global oceans of liquid methane. So Huygens was designed to float just in case it had to splash down, you know? So this is probably an ancient lake bed because, I mean, what else causes a rock to be that round? I don't know. Okay, so next we're going to look at, does it have, thank you for indulging me, by the way. We're going to take a look at if it has primordial soup. So first up, does it have water? No, but it does have liquid methane. And like I said, the quality that we love about water so much is that it's a liquid that can dissolve things. And methane is also capable of that. But, you know, we can't say anything for sure. We came from water. We have no idea what life would really be like if it, you know, came from methane. But it's an interesting thought. Next up, we're looking for chomps. Does it have chomps? No, it has chomp again. So just because it doesn't have that extra sulfur doesn't mean that it's not there. We just haven't detected it yet. So hope is alive. Next up, we're looking for energy source. Now, Titan, you know, it's orbiting Saturn. It is much further from the sun than we are. It is receiving, you know, a lower percent, much lower percent of light that Earth is receiving, but the sun is very powerful. So we're going to go ahead and say that it still has an energy source. It can still receive sunlight. It still makes it through the atmosphere. If light didn't make it through the atmosphere, you wouldn't be able to see anything in that video, right? So it has an energy source. Next up, we're looking for a radiation shield. We're going to go ahead and say that it does because Titan is sort of protected by Saturn's magnetic field for like 95% of its orbit. We don't know if the extra 5% is like detrimental or not. But it also has like this crazy thick atmosphere. So that's going to do some good for the potential of life on the surface. Next up, we're looking for time and stability. Yeah, 100%. It's formed at the same time as the rest of the solar system. The surface is, you know, stable, it's solid. We're all good there. So we reviewed Titan. Now we need to look at Mars. So this is our good little red planet friend. And it's a really weird place. And funny enough, it's actually the only place in the entire universe that we can say with 100% certainty is entirely inhabited by robots. And we know that because we put them there. So these are real pictures actually on Mars' surface of some of the rovers that we have. So in the top left and bottom right, these two are Perseverance and Curiosity. They both have selfie capabilities. They have an arm that extends, turns around a camera, takes a picture. And Perseverance over here actually took a selfie with little Ingenuity, which is in there in the top right. It's basically like a little Mars helicopter. It flies around. It's pretty cool. Then in black and white, there you see the shadow of Opportunity. Then in the bottom left here, you see little Sojourner becoming acquainted with that rock. So let's take a closer look at Mars. I've said this before, but I'll say it again. It's about half the size of Earth. It's a desert planet. It's very cold. It's very dry, very dusty surface, lots of fine grains moving around. And it has its red color because the dust on the surface is iron oxide. Iron oxide is rust. Mars is literally a rusty, dusty place. We still love it though. Some other things about Mars are that it has these really extreme surface features for its size. It's kind of a world of extremes, which we'll talk about. Another thing is that it has a thin atmosphere, not a lot, but it's there, made of carbon dioxide and nitrogen, which is pretty similar to our atmosphere. So I said it has a surface of extremes. Let's talk about it. This is an elevation map of Mars. So what you can see here is in red and white are the highest regions, with white being the tallest, and then the blue and purple regions are the lowest. So one big thing is there's this huge red region right here, and it's really high, and it's called the Tharsis volcanic region. And there's no geologic activity that's currently happening on Mars, but there obviously had to be because there's literally no other way to get something like that with a bunch of volcanoes. All these little white spots are volcanoes. And the one on the far left in the top there, that's called Olympus Mons. It's actually the tallest peak in the entire solar system. It is 3 times the height of Mount Everest. It's huge. And another thing you're going to notice is this giant crack in the surface. That is a huge canyon called Valles Marineris that spans the length of the continental United States. There's no other way to get something like that unless you have plate tectonics and things moving apart. That's not just liquid erosion. Last but not least, another crazy thing about this is look at the North Polar region at the top. It's all blue. It's all kind of low. This is indicative of perhaps global oceans that used to exist on the surface of Mars. And we have some pretty damning evidence that there was liquid. That's an ancient river channel. I don't know what to tell y'all. This is really, this is pretty damning smoking gun evidence. I mean, we know for sure that Mars used to have water for a lot of other reasons, but I mean, look at that. Another picture. So this is, you know, sediment being deposited by liquid moving. That's exactly what's happening here. So we know that it used to have water, and we know that it used to be geologically active, but nothing's happening now. So why does it look like this? Something catastrophic happened, but like, let's talk about what it looked like before first. So it definitely had global oceans of water, had a rocky surface like it does now. It had a thick atmosphere, and it had a global magnetic field. It doesn't have those last two things anymore, or the first one, quite frankly. So what the heck happened? Well, 3.8 billion years ago, the interior of Mars cooled down, and that means Mars lost its magnetic field. And basically, it cooled down because it's small. Things that are small cool down a lot faster. And what that means is its, you know, charged little core couldn't keep spinning. Things cooled down, and it stopped spinning, and it immediately lost its magnetic field. And shortly after that, it lost its atmosphere and its surface oceans. So the thing about a magnetic field is it's really helpful for keeping an atmosphere. So when that disappears, all of a sudden, all these really powerful rays from the sun can easily just strip away your atmosphere, especially when you're as close to the sun as Mars is, like we are. Yeah, so the timeline's a little fuzzy here, but it couldn't have taken, you know, longer than a few hundred million years. And remember this 3.8 billion years number? That's important because that's about the time that the period of heavy bombardment ended for the terrestrial planets, us and Mars, and Venus and Mercury. So that's about the time that we think life could have had the opportunity to start forming on Earth. So it's an important number. So if oceans left, where on Earth did they go? Excuse me, where on Mars did they go, actually, is what we're trying to answer. So there's a couple different theories. They could have frozen like immediately and then been buried underneath rock and sediment. They could have, you know, escaped to space. All of a sudden, there's no more surface pressure keeping the liquid there, so it might just leave. Or it could have seeped through the crust a little bit and, you know, stayed there. There's probably some combination of all of this that went on, but what mostly happened is a lot of it just sort of escaped to space and it doesn't exist anymore on the surface of Mars. So let's review. Well, okay, the question then becomes not, does Mars have primordial soup, but rather, did Mars have primordial soup? So we're going to try and answer that instead. Did it have water? Yes, 100%. 2, did it have chomps? Yes, it had chomps, and it still does. Did it have an energy source? Yes, just like us, it had the sun. Did it have a radiation shield? You know, it did, but not for very long. It had one, which was pretty awesome, but that also, you know, gives us a big question mark for time and stability. Like, yeah, it has a surface that has stability, but did that magnetic field stick around long enough, hold on to the atmosphere long enough, hold on to the liquid surface oceans long enough in order for life to form? And that's a really cool question because if we, you know, find fossils on Mars, answers a lot of big questions for us about how long it takes life to form, where else in our solar system life could possibly be. So that's why you should keep studying things like Mars. So we've looked at all of our contestants, and I said that this would be a talk about life in the solar system. So I would be remiss if we didn't talk a little bit about what could life possibly look like outside of Earth. Does it look like us? No. We are definitely the only humans in the solar system. We would have seen them by now. So you may be thinking, you know, we've talked about some water worlds here, like, you know, Enceladus and Europa, they both have these global oceans with hydrothermal vents. So could life look something like this? Could it look like the deep sea creatures that we see in the oceans of planet Earth, or maybe something fictional? It'd be a really cool thing. It's a really interesting thought, but I'm gonna have to go ahead and say probably not. What life does, if life exists outside of planet Earth, it probably exists in a microbial form. some sort of bacteria, something simple, maybe not something incredibly diverse like this. And I hate to say that, but as astronomers, we have to be really careful about what we say with 100% certainty. We just don't know enough to say anything with 100% certainty in regards to this. I mean, like, could you imagine if NASA was like, hey guys, life exists and it looks like this, and then later they found out they were wrong and they're like, oops, sorry, never mind. Like, we would never see funding ever again. None at all. So I'm gonna have to go ahead and say that life is probably microbial if it does exist outside of the solar system. So once again, we're coming back to our question, does extraterrestrial life exist in our solar system? We've reviewed a lot. What's the answer to this question? Maybe, maybe, isn't that an awesomely unsatisfying answer? We're, you know, maybe, but if life does exist, I can tell you that its most likely hosts are going to be Europa and Enceladus, these two water worlds. So these are our winners of our little competition here. The subsurface oceans of Europa and Enceladus are pretty promising for, you know, containing primordial soup. There is still a lot of unknowns. There is still a lot to discover, not just within our solar system, but beyond. But I personally am cautiously optimistic that life is not unique to Earth. So with that, thank you for listening.
Damn. That was really good. Scared about my job. Question?
Thank you. There is your answer. So great question. Honestly, no, because I said that, you know, the diameter of Mars is half that of Earth, and that half means a lot when it comes to the actual size and how much material there is inside of our planet. So I don't think that Earth is really at risk of cooling, at least anytime soon. Definitely not within our lifetimes, and maybe not even within the lifetime of the solar system. Right now, our sun is about halfway through its lifetime, so it has another about like 4, maybe 5 billion years left before it sort of explodes and kills everything. But I would say that no, we're not quite at the same risk that Mars was. Right. So we call it the period of heavy bombardment because it was pretty bad. It was pretty chaotic. I don't know the specific statistical numbers, but I can tell you that it was enough to keep the surface fairly molten. It would have been I mean, the problem was, yes, it was getting hit, but maybe almost the bigger problem is that all of those collisions were causing so much friction that it kept the surface so incredibly hot. Like, not just hot rock, but in a lot of places, literal magma. There was tons of volcanism getting stirred up. So it was getting bombarded a lot. But perhaps the larger problem from preventing life to form then was just how hot all of this stuff was. Any other questions? Okay, so what I can say is that in no peer-reviewed scientific article has the presence of life been confirmed on the surface of Mars. But what probably...
Well said.
Exactly. You know, like I said, we can't say anything for certain until we're 100% sure. But what probably happened with that is that, I mean, I don't know if some of you have heard of this, but there's this little microorganism called a water bear. The technical definition or the technical name is a tardigrade. It's this very incredibly robust microorganism. Like you literally can't kill it. It can exist in outer space. And we actually think we may have accidentally sent some to Mars. Because we've been to Mars. You know, we send things there all the time. And tardigrades can go dormant and exist on the outside of spacecrafts. Like they're unkillable. So if there is a meteorite from Mars that landed on Earth and had tardigrades in it, we'd be like, yeah, that's our fault. So another thing though, with people claiming in articles that life does or does not exist, a lot of times the signs for life are there, things that could potentially be the byproduct of life, but could also potentially be not. So that's how you get a lot of these sensational articles. Like, for example, like certain isotopes of carbon, biologists say that, life forms these certain isotopes of carbon, but they can also form from UV rays hitting carbon. So like there may have been signs of life, but there was no confirmed there is life on Mars. Anything else?
Up top. Oh, I'm sorry. Up top.
Yes. Okay. So there's a couple different theories about this, and I must give you a disclaimer. I am not an astrobiologist. That would be a question for an astrobiologist, I can tell you that, but I will do my best. So we're saying that it couldn't have taken any longer than a few hundred million years because heavy bombardment ended 3.8 billion years ago, and the oldest fossils that we have found are 3.5 billion years old. So that leaves 300 million years of gap there. And the stromatolites had to have formed, but we're not sure quite how long that took. We're not quite sure where in that gap of time that life began to coalesce. And so that means we don't know how long it takes life to coalesce. But some people believe that if the elements and the primordial soup conditions are there, life must form. Some people believe that there's a certain amount of chance in there. There's probably some statistical models out there for the randomness of whether or not life will form if conditions exist. But I can at the very least tell you at most it should take a few hundred million years, which I know sounds like an insane amount of time, but on astronomical timescales, because we're always talking about really, really long things, and a few hundred million years kind of isn't that long. But I wouldn't be surprised if it took less time for life to form. Is that satisfying enough? Okay.
Question, I see your hand over there.
I know. Okay, so I personally, this is a personal thing. I personally am of the belief that if there is life, we should let it be, and thus it follows that if there is not life, we should also let it be. That's me personally. There's probably other people that disagree with that. But in terms of, barring feasibility of dropping these elements in places like the subsurface oceans of Europa and Enceladus, also I would like to say they might exist. They might all exist. We just haven't detected them yet, which is why we keep funding science, so we can discover these cool things. Yeah! Love to see the support. So if the conditions of primordial soup exist, those are the conditions of life. Like I said with the previous question, we don't know if there's an element of chance in there. I'm sort of more of the belief that if the conditions of life exist for life to form exist, then it should probably form, because why wouldn't it? But I would think that it's probably an ethical issue. And there's also the matter of time. So, I mean, if we dropped a payload of certain things that life needs on one of these worlds, like, I mean, we're not going to be around long enough to see life form. Like, right. So, it's an interesting thought, at the very least. Any other questions that we can take or stop?
Let's do one more.
Okay.
We can do one more.
Cool. That's great to know.
Something that thing isn't getting published in the future.
Complicated
Actually,
feelings with nature.
Going back to that one plot that was
Oh, yeah. Oh, are you talking about the fossil? Or are you talking about Enceladus? This one? A different one?
one more.
The only thing I have from like published, I think, in Nature was that picture of Enceladus's plume.
Yep.
Okay. Got it. On. I don't know if I quote. So this is NASA JPL Cassini spacecraft data, but this image was published in a Nature article. Oh my God. Where are you sending me? This is the methane. Let me. I don't know if this was in Nature. Oh, it's in there. Citations, everybody. This is why I keep citing images.
Nature. Or for publishing in Nature, where I could make this ticket in Microsoft Paint.
Oh my God.
I'm sorry.
God.
Thank you so much. I wish I could take the telescope out and show you something, but we can't. So please enjoy the best beer in Atlanta. Ask questions. Thank you so much for coming.
Am I red? Because I feel red. Yeah. Okay. Everybody, I'm gonna